All right, welcome Cosmology from Home viewers. I'm Steffen Hagstotz, and together with Robert Reischke, today we will tell you about fast radio bursts, what they are, and what they can do for cosmology. All right, and to dive right in, so this is the overview of our talk today. We will start with very briefly talking about some of the current hot problems in cosmology. And later, we will also talk about how fast radio bursts hopefully can address some of those. Before we do that, we will also tell you what fast radio bursts actually are, what we know about them, and spoiler, it's not too much yet. Okay, so after that, we will tell you more about cosmological applications, and that's mostly using them as a measure for the expansion history or for the background. And then we can also probe cosmological perturbations with them, especially the electron distribution and why that's interesting. All right. Okay, so where are we now in cosmology? I think we have two big challenges right now. I mean, we always have the big question. We want to know what dark matter is and so on, and dark energy. But I think there are two very pressing issues. Okay, so one is, of course, the Hubble tension. Right now, we don't really know how fast the universe expands, and that's a bit of a problem. So different measurements based on standard rulers or Cepheid-calibrated supernovae give different results. And we would really like to know which one of these measurements is actually correct, or both. All right, and the other big problem right now is that in cosmology, we are very lucky to have all of these very, very big surveys that begin to take data now. But it comes with a lot of responsibilities. And the problem is that all of these big surveys will measure very small cosmological scales. And at the moment, we don't really know how to model these scales and how to get information out of them. And the main problem that stops us from analyzing these is that we don't really understand what the baryons are doing in the universe. Okay, so there's this problem of baryonic feedback, that there are processes in the universe that happen on very small galactic scales, but they affect the matter distribution on very large scales. And these processes are not well understood, and we can't model them very well. And if we can't model them very well, then we can't use most of the very nice measurements that we're going to take over the next few years. All right, and this is kind of an example. This is already what's happening now. So this is the data vector measured by the dark energy survey. So you see here these lensing correlation functions. It doesn't matter exactly what they are, but the shaded blue regions are the regions that the dark energy survey has to cut from their data vector, just because they are not confident in modeling those scales. And if you extrapolate this, it's half of the data vector roughly, but on small scales, there's a lot of volume in Fourier space. So this is 90% of the modes, of the Fourier modes, that are very well measured by the dark energy survey at the moment, but that can't really enter the cosmological analysis yet. And of course, in the future, this will only get worse as our measurement precision increases. Okay. So this is a plot showing the statistical errors that Euclid is going to achieve in the measurement of the cosmic shear power spectrum. And you can see that this gray arrow band is getting very, very small indeed. And the problem is that different models of baryonic feedback are bring much larger differences in the power spectrum than our statistical errors. Okay, so right now, this is a kind of simplified view because we don't really know, this is a one feedback model and we can vary the feedback strength. The situation is even worse, right? Because we don't know which model even to take, and not only how strong feedback is. But this just illustrates the problem. We really have to do better to get most of all of these surveys that are ongoing right now in cosmology. All right, and before we come to fast radio bursts and how they help to solve all of these problems, Robert will actually tell you what they are.
Yes, exactly. Also welcome from me to all the people at home. Yeah, the first thing about fast radio bursts you need to know is that basically everything about them is in the name. They are fast, so very short duration, microsecond. They are bursty, and they're in the radio. So they're very bright. They are in frequencies of 3,300 megahertz to 8 gigahertz. And that's basically what we know about them. They were first discovered by accident in archival data in 2007, and the mechanism is still debated. What we know, though, is that most of them come actually from extragalactic origins, and so far we know roughly 800 events, but in the near future we will have several thousand. Another thing that is important to know about fast radio is that some of them are actually repeating. So these 800 events also include some repeating events, right? Which is essentially the same source, but the burst is repeating in time. So if we look at the proposed mechanisms, there are a lot of them, from magnetas or AGN or mergers, neutron stars, can be anything. We look, for example, things that fast radio bursts come from aliens, but there are a very wide range of proposed mechanisms, and none of them has been proven definitely. Another thing to look at is the energy scale of fast radio bursts. So in this plot, we show the distance against basically the energy of the observed fluence. And you have supernova in the top right of this plot, and you have fast radio bursts a bit lower. So with a bit lower energy, or significant lower energy than supernova, for example, but still very, very large energy, so that you can actually see them over cosmological distances. So talking about the 800 events we know so far, I will show this plot on the next slide a bit bigger and with more detail. But until now, most detections are mostly incidental. But in principle, one would expect thousands of FRBs each night over the whole sky. And moving on into the future, we have now dedicated surveys for FRB searches. For example, CHIME or ESCAP is doing this, and also the DSA 110 telescope, which will be updated to the DSA 2000 telescope in the future, which are expected to provide 50,000 or multiple thousands of FRBs, which then can be used for astrophysical or cosmological analysis. Here's this plot, a bit bigger. So you see that CHIME in red dominates the known FRBs. There are also other telescopes which are just green, and then ones with host are marked with these crosses. One thing to see is basically that the events are generally uncorrelated with the Milky Way, so which adds to the conclusion that they are of extragalactic origin. So what is now the interesting concept behind fast radio bursts, or what is the primary, especially from a cosmological view, what is the primary observable? So what I show you here on the left side is the pulse, the radio pulse, and I show it in the frequency and the time domain. What you can see is that this black line undergoes a dispersion, and this dispersion or the time delay is very typical just because the photons scatter from the free electrons along the line of sight, and it follows an inverse square law. And the proportionality constant is called the dispersion measure, and it's dubbed dm. And it's just given, you take the electron density, you go to the rest frame, and you integrate along the line of sight, which is this equation below here. We can also look at the pulse structure itself. So what I show here is the dispersed. So I take the pulse and I divide out basically the dispersion. I look at the interval structure of the pulse, and this is shown here for a couple of radio bursts, and the pulse structure is at the millisecond level. And this suggests basically that the sources cannot be very, very big, right? So they must be of the order of a few hundred kilometers. Okay, so let's go back to the dispersion measure. So quite generally, the dispersion measure is constituted out of three components. It's the Milky Way component, so the dispersion the photons pick up in our own galaxy. Then you have everything between, which we call the large-scale structure component, which is the dispersion picked up in the large-scale structure, and a component which comes from the host galaxy where the fast radio burst originates on. So the Milky Way model we know quite well. You can check this accurately with pulsars, unless the burst is really like in the disk of the Milky Way and goes all the way through, then it might be difficult. The host halo models, they can depend on galaxy type, maybe, or surely they will depend on the position of the FRB within the host galaxy. And this is, in that sense, kind of a nuisance, but we will see also later that you can actually use this information to learn something about the galaxies itself. The interesting thing, though, is that these different contributions scale differently with redshift. So the Milky Way contribution is constant, obviously. The large-scale structure contribution is this integral over redshift, and the host dispersion scales with 1 over 1 plus z, just because of, again, rest frame conversion. There might be some residual scaling, but this is subdominant compared to this one. So what we learn from this is basically that if you have a lot of FRBs and you have identified hosts, that you can use statistics to tell these different contributions apart and therefore learn something about cosmology. So let's, from a cosmological point of view, write the large-scale structure contribution in a bit more detail, because this is the thing we are mostly interested in, at least. So we just express the electron density, Ne, is an ionization fraction times the number of baryons divided by the proton mass, right? And we can then expand the baryon density in a background quantity, which is the one here, and the perturbations, which depend on the electron bias, so how electrons are distributed relative to the density contrast of matter, which we call delta M here. And we will see these things becoming important in the next sections. For example, the density field will be part of constraining baryonic feedback, or also just constraining the electron distribution in the universe. You can learn something about the ionization history. You can use the fast radio bursts as a distance measure, because it's an integral over the line of sight. You can measure the baryonic fraction, which was famously done to addressing the missing baryon problem. But for some of them, you for sure need redshift. So you need the host identification of the fast radio burst. For the density field, when you do clustering, you can get away a bit with not knowing the host exactly. But we will come to this later. Okay, now I give back to Steffen to talk about the expansion history with fast radio bursts.
Thanks, Robert. Exactly. Okay, so what you can do with fast radio bursts is something very similar, actually, to what you can do with supernovae if you use them to measure the expansion history. Okay, so how this works is we just look at the mean dispersion measure that's expected at a given redshift. Okay. And the idea is simple, that like the further away you go, the more electrons are on average between us and the source. Okay, this is just this integral over the electron density. And exactly as Robert showed before, the electron density is just connected to the average baryon density in the universe. Okay, so if we rewrite this line of sight integral, just in an integral of redshift, then this makes the dependencies more clear on cosmological parameters. So we have a part of this integral that just really measures the expansion. Okay, so this E of Z. And we have a prefactor total amplitude of this integral, and that depends on either the baryon density or the Hubble constant. Okay, So you can measure basically one of those using fast radio bursts and mapping this average dispersion measure redshift relation. Okay, so people can basically choose one or the other. What we are mostly interested in at the moment is to combine this with some other knowledge about the baryon density coming either from the CMB or from Big Bang nucleosynthesis, so independent measurements of the baryon density. And this turns basically this whole relation or this measurement of the overall amplitude of this relation into an effective measurement of H0. Okay, so this is how you can do this. But as Robert said, it's crucial that we actually have redshifts for these events, okay? And so we are very lucky that now we have these dedicated fast radio burst searches going on. And with radio telescopes, you can achieve very, very long baselines and really excellent angular resolution. So one example is shown here. So this greenish plot, in green colors, this is an optical image from SDSS. The red cross shows you the center of this galaxy. And the white circle is the uncertainty in the position of this particular fast radio burst that was identified. Okay, so this is very, very, very accurate measurements. So below arc-second resolution. And in this case, then it's really possible to identify the host galaxy. We're not always that lucky. Okay, so far, actually, there are not that many fast radio bursts that have corresponding host identifications. But with the ongoing and future radio surveys, we expect actually to get host information for a lot of the events that are discovered just due to these very long baselines. Okay, and if you measure your dispersion measures and your redshifts, then basically you're already done, right? Like you compile this average dispersion measure redshift relation. So in this case, we already corrected for average host contributions to these. And you get this average relation, and that more or less can tell you directly then the Hubble constant in this case, okay? So if we go to the next slide, exactly. So here we see kind of a posterior for the inferred Hubble constant from every single event. And because they're all fairly broad, but consistent with each other, so you can combine them and you can get this black constraint here, which is a measurement of the Hubble constant to like 10–15% level, okay? So what really, and just to compare, like this is what you can do right now with gravitational waves. Okay, so this is the GW 170817 with an optical counterpart and gravitational wave measurements. And right now, fast radio bursts really are actually much better. Okay? What dominates our errors here is really the uncertainty in the dispersion measure that comes from the host galaxy. Okay, and this is a recurring topic, and we will discuss this several times throughout the talk. There are independent other analysis, and they luckily get similar results to ours. Okay, so all of these measurements basically give you something like to the 10–15% level, but this is limited by uncertainty in the host dispersion and really statistics. Because, okay, so you can just estimate basically when you measure more fast radio bursts, and we expect to get a lot more in the future, also with host identification, then just the statistical error on the Hubble constant goes down considerably. And the most important point is that with those samples, actually, you can relax some of the assumptions. And as Robert also said before, statistically, you can tell these different contributions to the dispersion measure apart. So you can use your sample to calibrate for the host dispersion. So this is a forecast that we did recently. And we show that with 500 events, you can get very, very precise measurements of the Hubble constant, but also of this host dispersion. So you calibrate the dispersion redshift relation with the data itself. okay? Just because these things, the large-scale structure and the host dispersion, scale differently. All right. There are other ideas what you can do with fast radio bursts. So Robert also showed this distribution of energies before. So this is just what you get if you basically plug in all the FRBs that we discovered so far. So FRB spectra don't, FRB signals don't show any clear spectral information. Okay, so they're not always in the same wavelength. We don't really know what the mechanism is. But, and the energy distribution also varies wildly. But the idea is that even if this distribution will differ from one event to the other, the overall distribution will have some cutoff. There will be some maximal energy that you can get out of the FRB mechanism, whatever it is. Okay? And if you know this cutoff, or if you can calibrate it from the data, then you can calibrate this and turn them essentially into something like a standard candle, okay? And this works very similarly for the experts, just for this tip of the red giant branch method to calibrate the distance to supernovae, okay? So we think like the tip of the FRB luminosity plot is maybe an interesting distance proxy, and this was also explored in this paper by James et al. All right, okay. But apart from just looking at the background expansion, there's a lot more you can do with fast radio bursts, and Robert will tell you all about it.
Yeah, thank you, Steffen. Going back to the fast radio burst and the dispersion measure, if we look at these two events here, one here and one here, of course, the photons of these two events will traverse the same or similar large-scale structure, which itself is correlated, and therefore the dispersion measures between those two lines of sight will also be correlated. And the first thing this will do is that if you do this DMZ diagram Steffen was showing you, you will not have independent data points, but the different data points in this dispersion measure redshift diagram will be correlated. And we calculated this in a paper a year ago, how big the covariance between these data points is, and if it has an influence on current data. The short answer is it doesn't, but if you collect more and more fast radio bursts, if you have like 500 FRBs, you will see an effect if you neglect this correlation. So there one has to be cautious, but one can actually also use this correlation, and this is essentially what this whole chapter is about, to constrain different physical models. So for example, what you can do is you can constrain the equivalence principle. And I again show here the covariance matrix, or the correlation coefficient of the covariance matrix. And on the left side, we see how the correlation coefficients look like if the equivalence principle holds, and on the right side, how it looks like when it doesn't hold. And we see that that there are large correlations on the off diagonal. So you basically take this DMZ relation, which you saw for the Hubble constant, and you let the errors tell you something about the equivalence principle. That is the main idea of this paper. However, you can of course even go further, and you can kind of use the the clustering of the fast radio bursts of the dispersion measure, the correlations itself, as a signal, or cross-correlated with the large-scale structure itself. So there are two very nice papers, one from now, already 3 years ago, from Chime, where they cross-correlated the positions of galaxies from different surveys, from DESI and WISE, for example, with the positions of fast radio bursts. And they could find some kind of correlations. Of course, they don't have that many FRBs, so shot noise is still very high. But by this, you can basically constrain the location of fast radio bursts if you don't have redshift information, just by statistical cross-correlation with a galaxy survey where you have spectroscopic information. Another application was done in Flim-Flam a few months ago. And what you can see here is these different panels show different FRBs. And the dots are basically targeted observations of galaxies along these sidelines, and these observations are then used to reconstruct the density field along the sideline of the fast radio burst, which essentially reduces cosmic variance and allows a better constraint on, for example, the Hubble constant or the expansion function, just by reducing the error on the measurements, which is dominated by cosmic variance. And they find they can reduce cosmic variance for some FRBs quite a bit, depending on how densely they sampled the galaxy field in front, and therefore the density field, to reduce the cosmic variance with constrained realizations. But the big point we would like to make is that we go back to baryonic feedback. So this is a plot Steffen already showed. And as a reminder, it shows basically the ratio of the power spectrum of weak gravitational lensing when you include baryons compared to when you don't include baryons, when you only have dark matter. And you see this very strong suppression, and we choose one feedback model to scale the suppression. This is shown in the color bar. And Euclid statistical error bars are shown as this gray band. And the problem is, of course, if this is the situation you have to deal with, you have to dump all this precious sensitivity of Euclid on these small scales into constraining the feedback. And you have nothing left for cosmology, which then begs the question, why did you do this in the first place? So what you can do is you can include independent probes to measure the baryonic feedback. So mostly at the moment, it's measured via the Zanjarov-Sedovich effect, because this is dominated by hot gas in galaxy clusters, and this is therefore also an excellent probe of baryonic feedback. But of course, also fast radio bursts, since they probe with the dispersion measure, the integrated electron density, so the baryon density kind of, they will be much more susceptible to baryonic feedback and therefore much more sensitive to feedback mechanisms than weak lensing alone, which is very sensitive to the total matter distribution. And an interesting aspect also compared to cosmic shear or weak gravitational lensing in general is that you don't need that many fast radio bursts to do a statistical analysis. As I show on the left, I show basically two surveys of equal signal to noise. So the noise is relatively of the same magnitude as the signal. And in order to do this, I show the shape noise for KITS, for the kilodegree survey. And in the kilodegree survey, there are around 50 million galaxies. In order to get the same significance, you only need 10,000 fast radio bursts, right? Just because the intrinsic scatter in the dispersion due to the host contribution is much smaller than the intrinsic scatter in the ellipticity in weak gravitational lensing. Okay, so you can then mock up basically a forecast for an experiment where you use Euclid-like data and you add these 10,000 FRBs and you measure the cosmic shear signal, you measure the cross correlation between the cosmic shear and the dispersion measure, and you measure the dispersion measure autocorrelation. And this was then done together with Dennis Neumann, a master student of mine, who is now in Leiden. And here we show basically in purple the constraints you can get for Euclid weak lensing alone, and the green contours are when you add fast radio bursts. And what I want to highlight is the log T AGN parameter, which controls the strength of the feedback. So larger log T AGN means more feedback. And you can see that fast radio bursts do way, way better than Euclid weak lensing alone and can break basically this degeneracy with baryonic feedback, which, for example, helps to improve measurements on the mass of the neutrinos. So going back to this plot, if we add fast radio bursts, we can basically constrain this whole family of feedback models here, or this, so it's one family of models, but we can constrain this whole prior range we would have in principle to this green band here, which will help Euclid or LSST significantly to boost their cosmological constraints. However, there's also another method to constrain baryonic feedback, and since Alexander is a master student of Steffen, I will give this back to Steffen.
Yeah, exactly. Okay, so So Robert already explained how you can measure these feedback properties from the correlations of this large-scale structure component of the dispersion measure. But whatever happens at these host galaxies also is connected to baryonic feedback. So Alexander Theis did his master thesis on this. What he did is that he explored the properties or this host dispersion measure for galaxies that he extracted out of different simulations. So what is shown here is this distribution of host dispersion just in different implementations of baryonic feedback models. And you can see that they vary a lot. Okay, so all of these simulations predict different properties of the host galaxy. Okay, so this should quite scare you, okay? Because that means that we can't predict the properties of these galaxies very well. We just don't know which one of these models is really correct or not. But you can always turn this around. With enough FRBs, we can just let the data decide which one of these models is actually the best description for the data that we find. Okay, so in this sense, you can also use information from the host dispersion itself and infer the different baryonic feedback models.
Yeah, thank you, Steffen. So the last part of our presentation is the mandatory machine learning or neural network, or however you want to call it, section, which is very on vogue in cosmology very recently, with also good reason. And what we did is now is to give up basically the likelihood assumption. So our goal is to do simulation-based inference without assuming a likelihood. So most of the time, what you assume is a Gaussian likelihood, for example, or a log normal likelihood, and it's very difficult to incorporate systematic effects in these things, and which will become important with more and more data. So the idea is that we start basically at the host and we draw from some host distribution which has a physical model. Here we choose a log normal model. We draw a dispersion measure. And we do this for each fast radio burst basically in our catalog, for which we have a host identification. And we have basically a realization of the host contribution. And then we place these FRBs in log normal, in log normal mocks, which are generated by glass. So here I show you on the right side realization of these log normal mocks. So we place the FRBs in there, we add the host contribution, and then we integrate along the line of sight. And we basically get a simulation-based prescription for the dispersion measure, or for realization of the dispersion measure of that FRB. And all this stuff was mainly done by Christoph Gunnar, who's a master student of mine who is currently looking for a PhD in cosmology. So reach out. In any case, we then have this simulation-based pipeline, which I have in a bit more detail here. So we have our cosmological parameters on the very top. We predict the linear matter power spectrum. We use a Halo model code to predict the nonlinear matter power spectrum using a feedback model, and we can basically also predict the electron bias with this by just predicting the electron power spectrum as well. And we then create essentially these spherical shells. And we then use the data from the FRB catalog to place the fast radio bursts in these shells. We simulate the DM, we add the host contribution, we do a data compression, and then we do simulation-based inference using machine learning. So we basically, from this, we create a lot of simulations, and then we learn the joint distribution of the data and the model parameters theta. And at the very end, we make a cut basically at the data and sample from that posterior without having assumed any posterior in the first place or any likelihood in the first place. And the preliminary results here are shown. And what we vary basically are three parameters. So this S lambda is basically the whole amplitude, which is in front of the dispersion measure redshift relation. So if it's 1, we assume the fiducial cosmology, which is consistent with Planck. And then we also fit basically the mean of the host distribution and its logarithmic width. And we all do this by plugging everything into our pipeline and get these constraints in the end out. And these constraints are on real data. And what we see is that we can kind of already constrain the shape of the host contribution already, which is very exciting with the FRBs we have at the moment, which is not a large number, which is around 20. So closing now, going back to the challenges in cosmology Steffen mentioned in the very beginning. So we have the Hubble tension, and the question, how fast does the universe expand at the moment? On the other hand, we have small-scale clustering and the issue with baryonic feedback, how can we understand the small-scale clustering and basically the transition, again, from cosmology from very large scales to astrophysics from very small scales, and how do we bridge this transition? And we would argue that fast radio bursts are an excellent candidate for this. First of all, we can measure the Hubble constant with them or the expansion history in general. But at the same time, we can also measure baryonic feedback, or we can, as Steffen just said, also try to measure basically the profiles of galaxies using the host contribution. And the more fast radio bursts will come in, the more, obviously, the more signal to noise we have, and we can disentangle these different quantities. And there's really, really a lot to learn from fast radio bursts. And with this, I would like to summarize what have we learned. So fast radio bursts are, well, we don't know what they are. The mechanism is unknown and under debate. But we know what we can observe from them, and we understand that we can observe the dispersion measure, and we know where it comes from, and we have a good understanding of this. And using this understanding, fast radio bursts can provide an excellent measurement of the expansion rate of the universe at the moment at the 10% level, which everything to do with fast radio bursts at the moment is not dominated by systematic effects, but rather by statistics. But many more events are coming in the near future with, for example, CHIME, ESCAPE, HIREX, or DSA 110. Also, we have shown you that the correlations are a very, very powerful tool to test fundamental physics. For example, you can test the equivalence principle, but most importantly, you can directly measure the impact of baryonic feedback on baryons and therefore constrain baryonic feedback models and the distribution of baryons in the universe, and also help upcoming surveys like Rubin LSST and Euclid to become the tools of precision cosmology they were promised to be. And with this, we would like to thank you.
Thanks a lot, and we're very much looking forward to the discussions and listening to all of your talks over the next days.
Thank you.